Welcome to the AI Research Roundup. I am your host, Alex. Today is May 11th, 2025. We're discussing an ICLR conference paper from just under 4 months ago. Safety alignment should be made more than just a few tokens deep. This paper finds that common LLM safety methods, like supervised fine-tuning or SFT, that's training on safe examples, and preference-based approaches like reinforcement learning from human feedback, often result in shallow safety alignment. Essentially, models learn to use refusal prefixes, those initial I cannot phrases, by mainly adjusting their generative distribution, how they pick words, for just the first few tokens, making them vulnerable. Alright, so this table really drives home the point about those refusal prefixes. It measures the harmfulness rate, that's the percentage of unsafe outputs, on a test set called the HX prefix I benchmark, when different refusal prefixes are pre-filled during decoding, meaning the model is forced to start its answer with them. We see two models, Llama 2 and Gemma, comparing their aligned or safety-trained versions against their base or original unaligned versions. Notice how even the base models become much less harmful, sometimes almost as safe as aligned ones, just by adding that initial refusal. This really highlights the shallow nature of the alignment. Okay, so building on that idea of initial tokens being key, this next figure really illustrates the vulnerability. It plots the attack success rate, or ASR. That's how often an attack results in harmful content. Against the number of harmful tokens the model is forced to start its response with. We see that for the aligned models, like Llama 2 Chat and Gemma IT, their attack success rate shoots up dramatically to over 50%, with just a few pre-filled harmful tokens. This really shows that if you can bypass those initial refusal mechanisms, the underlying safety training is easily overcome, further highlighting that shallow alignment. So this next figure provides more evidence for this shallow alignment. It shows the per-token Kullback-Leibler divergence, or KL divergence, which is a way to measure how different the probability distribution of the aligned model is from its unaligned base model for each token in the sequence. We can see for both Llama 2 Chat and Gemma IT, the Kullback-Leibler divergence is very high for the first few tokens, then drops dramatically. This really pinpoints that the safety alignment primarily changes the model's behavior right at the beginning of its response, not deeply throughout. Okay, so this figure delves deeper into how fine-tuning attacks exploit this shallow alignment. It shows 3 plots examining the per-token dynamics when fine-tuning Llama 2 Chat on harmful examples. The first plot, A, shows the per-token cross-entropy loss. That's a measure of how much the model's predictions differ from the target harmful text, token by token. The second, B, shows the per-token gradient norm, indicating how much the model's parameters are changed for each token. Both show the largest changes happening in the very first few tokens, where the original safety was concentrated. This makes it easy to undo the safety. Following on from how easily shallow safety is undone, this figure explores a potential solution, data augmentation. We're again looking at the per-token Kullback-Leibler divergence. The blue line, for the standard Llama 2 Chat model versus its base, shows that familiar drop after the first few tokens. But the green line represents a Llama 2 Chat model trained with safety recovery examples. These are training instances where a harmful start is deliberately followed by a safe refusal. Notice how its Kullback-Leibler divergence stays much higher across many more token positions. This suggests the data augmentation creates a deeper alignment, changing the model's behavior beyond just those initial few tokens. Alright, so this table really quantifies the benefits of that data augmentation. We're looking at the attack success rate. Again, how often an attack elicits harmful content for the Llama 2.7b chat model. Comparing the initial standard model to the augmented one, we see huge improvements. For pre-filling attacks, for GCG attacks, these are adversarial inputs designed to fool the model, and for decoding parameter exploits, where text generation settings are manipulated, the augmented model's attack success rate is drastically lower. For example, with 10 pre-filled tokens, it plummets from over 51% to under 3%. This clearly demonstrates enhanced robustness. So moving from data augmentation, this table details another strategy for deeper safety, fine-tuning with a constrained objective. We're looking at Llama 2 Chat and Gemma IT comparing their initial state, standard supervised fine-tuning, which is a common way to specialize models, and the author's constrained supervised fine-tuning. This constrained method applies stronger controls, or regularization, essentially rules that limit how much the model can change, on how the model generates those very first few tokens. The results are pretty striking. For fine-tuning attacks like harmful examples, the attack success rate plummets from around 80-90% with standard supervised fine-tuning to well under 10% with the constrained approach, while utility on normal tasks remains high. So to wrap up our discussion on this insightful work, it's clear that much of current LLM safety alignment is quite superficial, primarily tweaking just the initial few words of a model's response. This shallow safety, as the authors term it, leaves models open to various exploits. However, strategies like data augmentation with safety recovery examples and constrained optimization during fine-tuning, which involves carefully controlling changes to the model, show real promise for building deeper, more robust safety. That's all the time we have for this AI Research Roundup. Thanks for tuning in, and I am Alex, hoping you'll join us next time.